So we're given an arbitrary second-order linear differential equation, and we already know from some general theory that the solution to this equation is always of the form c1y1 plus c2y2, where these two functions, y1 and y2, are just any two linearly independent solutions to this equation here. Okay, so this begs the question if we can determine the functions y1 and y2. Since if we can, then we can solve the whole differential equation. So we won't be able to determine y1 and y2 from scratch, but we will be able to make some progress, and we will be able to solve the following problem, which is that if we are given a solution y1, can we determine another solution y2 from it, such that the pair y1 and y2 are linearly independent? And there is a solution to this problem, which works generally. It's called reduction of order. And that's really the topic of today's video. Okay, so what is the solution? Well, we're actually going to solve for a different function, a function u. And u is basically just going to be equal to y2 divided by y1. So we're going to solve for that function instead. Because then we can just represent at the end, if we can solve for such a function, then we can solve for y2, just because y2 is equal to u times y1. And we know what both u and y1 are. Okay, so let's see how this works in practice. So here we are. We're given a differential equation here, and we are given a solution, and the question is to determine a solution y2, such that the pair y1 and y2 are linearly independent. Okay, so here's how we do that. So the technique of reduction of order is to make this substitution here, to let y2 be given by this expression here. So u times y1, which in this case is just going to be u times e to the negative x. Then, because we want y2 to be a solution, we're going to substitute it into this equation up here. So we have to actually compute the derivatives, which is what's happening here. So the derivative of y2, because this is a product of two functions, is just given here. And then this is a difference of a product of two functions, and so the derivative of this, if you compute it, will end up being this. Okay, now we've computed the derivatives of our function y2, and so we can substitute it back into our differential equation here. That's how we are getting this expression. So into this differential equation, we just substitute y2. And so we get this. This here is just the second derivative of y2. This here is the first derivative. And this here is just y2. So then we know that since y2 is assumed to be a solution, we must get 0 here. And that's good because in this case we can have a lot of cancellation. Just to show you where. For instance, this here will cancel with at least one of these, and also there's another one here. So in fact, this one and this one will cancel the 2 and this, and then the u prime e to the x 2 u prime e to the x will cancel with this. And so in fact, all we'll be left with at the end is just u double prime e to the negative x equal to 0. And because e to the negative x is always positive, we get this, and that just means we can choose u to be equal to x. And so then, because we found u, we can write our final solution, y, which is equal y2, which is equal to u times y1, and that's just given here. Okay, now this technique I said works in general, and that means because it works in general, we can actually have a general formula for it. And so here it is. So given a solution y1 to our differential equation here, we can always set y2 equal to u times y1, and we know that the derivative here of u is just going to be given by this formula. Okay, so using this formula, we can determine the derivative of u, and then from the derivative of u, we can determine u, and then we can determine y2. Okay, but why is this formula true? Let's just take a look at why that is. The reason is because we make our reduction of order substitution here, Then we compute the derivatives just as we did in the previous example, but now we're doing it in general. So this is just the derivatives of y2 when this is what y2 is. And then substituting it back into this equation here, this is exactly the substitution. Here is just y2 double prime. This is y2 prime, and this is just y2 over here. And then rearranging so that we factor out u and u prime and u double prime, we actually just end up with a very simple expression, which is going to happen because this here is going to be 0. And that's really the main trick here. This is 0 because y1 is assumed to be a solution to our differential equation up here. If you look at this differential equation, if y1 is a solution, then this has to be 0 over here at the bottom. So then, in fact, what we'll be left with is just that this is equal to 0. So in fact, just this part of the equation. Great. Now we can let v equal u prime, and v if v is equal to u prime, then we can rewrite this equation that we got from the previous step here in a first order way, which is what's happening here. And then that can then be rewritten into this form here. Okay, and this is a very nice first order equation. We can solve it, and so solving it is just what's happening for the remaining steps here. So we integrate both sides. We get this expression here. Here we've just separated the fraction to get this, and then we end up with this, and now we can raise both sides of our equation to the power of e, and so we get v is equal to e to the negative 2 ln y negative 1, and so we just get this. Okay, and that's our formula. Okay, so let's just see how this formula works on an example. So suppose we're given this problem now. We have to find y2, where we're given y1 is equal to x here. And we know that y1 satisfies this differential equation here. Okay, so let's use our formula here. Firstly, we know that y2 is going to be of the form u times y1. And now we can use our formula to say that u prime of x is going to be equal to 1 over y1 of x squared. But y1 of x is x, so this is just x squared. And then we multiply this by e to the negative, the integral of p of x. And now we have to determine what is p of x. But we are not actually in a position to know what p of x is yet. And the reason for that is because we haven't yet put this equation in the form that we were using, that we need. The form up here is like this. There's no coefficient in front of the y double prime. So actually we first have to do that. And so we do that here. Here we're just going to get y double prime plus 2 of x y prime minus 2 of x squared y equals 0. Okay, now it's in standard form, and then we can see what the p of x is. Here it is. Okay. So p of x is just going to be 2 over x. We put the 2 over x here, dx, and we can solve this. So we get 1 over x squared times e to the negative 2 ln x. And so here you'll see this just simplifies nicely to e to the ln of x to the negative 2. And this here is just 1 over x to the 4. Okay. So that's what u prime is. So u prime of x is equal to 1 over x to the 4 implies that u of x, so we can now solve for what is u of x here. And so we just integrate both sides here. So all we're going to get is negative 1 over 3 x to the negative 3. And then finally, this allows us to say what is y2. y2 here is just equal to u times y1. so that y2 is just equal to negative 1 over 3 x to the negative 3 times here x, because that's what y1 is. And so this is just equal to negative 1 over 3 x squared. And x to the negative 2, sorry. Okay, so that's the technique of reduction of order. And this is used quite a lot in what follows. So we will use this formula in many of the problems that we'll do in future videos. Okay, thank you.